Welcome to Bricklayer. In this video, we're going to look at using level 3 put function calls to create rectangles having arbitrary dimensions. And I would like to point out before moving on that if you just limit yourself to rectangles, you can create a lot of really cool artifacts. The picture that you see here on the right is by a famous painter named Pierre Mondrian, who is well known for creating these kinds of paintings, and he's considered one of the greatest artists of the 20th century. Now, I would like to recommend that before watching this video, you go to Vitruvia and you do all of the exercises relating to concept 14. This will just help you understand the things that we're going to talk about in the upcoming slides, make it easier to understand. So in these slides, there's a couple things I want to talk about. One is I want to show you how you can convert from a level 1 and level 2 put function call to a corresponding to an equivalent level 3 put function call. And then I want to talk a little bit, take a closer look at how one can calculate certain cell positions given the lower left corner, the reference point of a put function call, and the size of the rectangle that you're creating. So it's important for us to be able to do this. All right, so I'll get back to that. So now let's just look at some conversions. So here's an example of a level 2 put function call. And the way you can convert this into a level 3 put function call, a corresponding one, is through a couple of steps. The first step is you remove the underscore symbol and you replace it with a blank. And then the next step, you take the dimensions, this 4x2, and you replace that by a tuple, which is a mathematical object. So parentheses 4, comma 2, close parentheses. Now notice that this tuple looks a lot like a coordinate. However, the put function is written in such a way that it says I accept 3 inputs. The first input is going to be a tuple, and I'm going to treat that tuple as describing the dimensions of a rectangle. Then the next input is the Lego brick that I'm going to use to create a rectangle having those dimensions. And the third input is the coordinate of the lower left corner of this rectangle, the reference point. So it's just that simple, but let's take a couple of more. Let's look at a couple of more examples before we move on. So again, it's just step 1, remove the underscores. Step 2, convert this dimension description into a tuple. Those are the 2 steps. Okay. All right, so that's the algorithm. Now I'd like to observe something, or actually make a couple of observations. First, the first observation that I'd like to make is that every level 1 or level 2 put function call can be mapped or can be translated to an equivalent level 3 put function call. I hope that sort of at least I've informally convinced you of this, but basically if I had to prove this, my proof would involve this conversion algorithm, and I would show you how you can use this to convert every last one of these put functions in level 1 and level 2. Another observation, perhaps this one's a little bit more important, is that not every level 3 put function call can be mapped back to an equivalent level 1 or level 2 put function call. And the proof for that is just by example. So if I can come up with a level 3 put function call that cannot be mapped, a single one, an actual instance that cannot be mapped back, then that's my proof. So here I have one that has dimensions of 3, 7, and there is no put function call that will place a 3 times 7 brick in level 1 or level 2. So the mapping just goes from level 2 to level 3, but not the other way around. And what you could do at this point, if you wanted some practice, is you could take all of your level 1 and level 2 programs and try to convert them to level 3 programs, so the put function calls. All right, so an important aspect of dealing with, what put function calls in level 3 provide us with is the ability to create large rectangles. And so prior to that, if you needed to place two bricks side by side, you could sort of count it out and you could visually inspect it and everything kind of worked out. It wasn't too hard to do. But now if you're going to create large rectangles, counting it out to make sure that what's the coordinate of the free cell that's right next to the rectangle that I just placed, counting that out is not a lot of fun. So there's an easier way to do this, and that's with math. So I'd like to start out by noting that two of the inputs to these put functions in level 3 are the size of the rectangle and the lower left cell of the rectangle. So we're going to use that information to compute positions of a variety of other cells. And these cells basically are ones that are of interest to us. There are other calculations too, but these are the basic ones. And so let me show you here on this picture what we might be interested in. So where the star is right now, that's the lower left corner. We can, by visual inspection, we can tell that this the dimensions of this rectangle is 5 by 3. And what we'd like to do is use formulas to calculate the positions or the locations of a variety of other cells, the coordinates of them. So maybe the corners of the rectangle might be interesting for us, but perhaps more interesting would be cells that are right next to, adjacent to the corners of these rectangles. And if we can do this kind of stuff, then a whole bunch of other cell calculations become pretty easy. It's just more of the same. So I'd like to start with a formula that I talked about in an earlier video, a video on circles and rings. And this had to do with if you're printing out, if you're sending to a printer, you want to print a document and you say, I want to print pages 6 through 9. The question is, how many pages are being printed? And the formula that we came up with is you take the upper page number, 9 in this case, you subtract from it the lower page number, 6, and then you add 1. So 9 minus 6 is 3, plus 1 is 4. So the size, the number of pages that you have printed is 4. Page 6, page 7, page 8, and page 9. And this same idea, the same kind of thinking works for figuring out the number of cells in a certain range. So if I have a cell whose x-coordinate is 9 and another cell whose x-coordinate is 6, and I say how many cells are there between these coordinates that include 6 through 9, what is this? Then it would also be 4 cells. So this idea works. This idea works for Bricklayer. So let me do a little bit of math and rewrite this formula a little bit. So first I'm going to flip around the minus lower and plus 1. And so nothing has changed in this calculation. Next I'm going to add lower to both sides of the equation. And then I'm going to simplify the right side. So minus lower plus lower is 0 and goes away. So that's simplified now. And then I'm going to subtract 1 from both sides of the equation and simplify again. And I get lower plus size minus 1 equals upper. And if I flip this around, this equation, I get upper equals lower plus size minus 1. And so this is the form of the equation that we are interested in when we're trying to figure out the coordinates of like the corners of a rectangle. And the free cells that are adjacent to that are just the corner plus 1, so lower plus size. So here, let's look at an example. So I have this put function call. I have the x size is 5, the z size is 3, x lower is 1, and z lower is 4. So this is the information that I have. And I have my formula from the other slide, from the previous slide. So I want to do a version of this formula for x of this equation, I want to do a version of this equation for z. So instead of just plain old upper, I'm going to have x upper. And instead of lower, I'm going to have x lower. So if I sort of come up with a new version of this equation, I get this, and I can now plug in numbers for x lower and x size and then do the math. And so then I realize that x upper here is 5. And I can do something similar for z. And again, I can plug in the numbers, and then I realize that z upper is 6. And so here's the graphical representation of that. So this is where x lower and z lower is, which in this case would be 1, 4. Here's the upper left corner, using this formula to figure this stuff out. Here's another interesting one, the free cell that's above, immediately above, adjacent to this rectangle. This is an important coordinate to be able to figure out if you're going to be placing rectangles side by side. And similarly, the lower right corner of this rectangle is just applying that formula, plugging in the right values and doing the math. And again, this one is an important one if you're going to be, this coordinate is an important one to know how to figure out if you're going to be placing rectangles side by side. So let me point this out again. It is x, the lower right corner was x lower plus x size minus 1, but we're going to go one step further now, one cell further to the right. And so it's not minus 1, that goes away. So it's just x lower plus x size. So x lower plus x size gives you the next free spot. All right, so armed with that information, I think we're in a position now to play around with some write some Bricklayer-like programs. You may want to watch this video more than once before you go on to the next video.